So for number 34, we're trying to find whether this geometric series is convergent or divergent. So the first thing that we're going to do here is we're going to rewrite the series as a difference of two different series. So what we're going to do here is just write it as the sum from n is equal to 1 to infinity of 0.8 to the n minus 1, and then minus the series that goes from 1 to infinity of 0.3 to the power of n. Okay, so once we're here, all we have to do is adjust the index on the first one, because when we look at these geometric series, we have r to the power of n. So to adjust the index, we have to think about what happens when we plug in n is equal to 1 to the power here. So if we plug in the first index, we're going to have 0.8 to the power of 1 minus 1, which is 0.8 to the power of 0. So instead of beginning at 1 and going n minus 1, since what we're actually evaluating here is 0 for the first one, we can just change it and go from n is equal to 0 to the power of n. Because you can see if I plug in 0 as my index, I'm going to get 0.8 to the power of 0, which ends up being the same thing. So these are equivalent expressions. Let me rewrite this. So once we are here, we can now analyze the geometric series. So geometric series has a form a, which is some constant, times the ratio to the power of n. So for the first one, a is just the number 1, which is being multiplied here. And the ratio is 0.8. Now, if the absolute value of the ratio, which is 0.8, is less than 1, which in this case is true, it means that this series here converges. And the reason that it converges is because if I take 0.8 and I raise it to a very large number, like say 1,000,000, that's going to go to 0, essentially. The limit's going to be 0. And as n gets large, the terms in the sequence, they get closer to 0, it means that I'm just adding 0, and so my total sum is not going to change. Whereas if the absolute value is equal to 1 or greater than 1, it means that if I take, say, 1.2 and I raise it to 1,000,000, that's going to be a very large number. So with every n that you add, your sum is changing, right? It's not going to stay fixed. So for the first one, the absolute value is less than 1, so it does converge. And for the second one, the ratio here, what is raised to the power of n, is 0.3, and that's less than 1 as well. So both of them converge. Okay, so if we look at this, we are almost ready to sum up this series where we're going to use this formula here. So the first series, it does match up perfectly with the formula because it begins at n is equal to 0. However, the second one does not because it begins at n is equal to 1. So to get it to match up, we just have to change it a little bit. And instead, what we're going to do here is we're just going to say, okay, instead of beginning at n is equal to 1, because when we plug in n is equal to 1 for the first index, what we will evaluate is 0.3 to the power of 1, right? So that should be our first item. So we're going to reduce the index to n is equal to 0. Now, if I just do this to the power of n, that's not going to work, because if I plug in the first index, it's going to be 0.3 to the power of 0, which is just 1. It doesn't give me the 0.3 to the power of 1. But I can adjust it by multiplying it by 0.3 outside, because if I do this and I plug in n is equal to 0, what I'm going to get here is 0.3 times 0.3 to the power of 0, which is the same thing as 0.3 times 1, which is just 0.3. And I'm just going to put here to the power of 1, and that would just match here the first input for n is equal to 1, which would be 0.3 to the power of 1. So if I reduce the index by 1, but then I multiply the whole thing by 0.3, we can see that the output is going to be the same. So we are just going to rewrite this as, so that is equivalent to, and I'm just going to copy this whole thing, and paste it here. And I'm just going to adjust the index. I'm going to begin at n is equal to 0, and then I'm going to multiply it by 0.3 outside. These are equivalent. So once I have this, I can now put it in the sum, right? So for the first one, our a, which is the number that multiplies outside, is just 1. You can think of it as being hidden here. So a is equal to 1. and r is equal to 0.8. Whereas for our second one, the number that's outside is 0.3, so a is equal to 0.3, and r is going to be equal to 0.3 as well. That's the number that's being raised. So let's plug it into the formula here. So we're going to have a 1 over 1 minus r, which is 0.8, and then minus the sum here. So a is 0.3 divided by 1 minus 0.3. So if we do this, we're going to get 1 divided by 1 minus 0.8, that's 1 over 0.2 minus 0.3, 0.3 divided by 1 minus 0.3 is 0.7. And so if we plug this into our calculators, what we're going to get here, it's going to be, that's going to be 32 divided by 7. So this here is the result of the first series, and then minus the value of the second series. So once we've adjusted the index, and we use this formula over here to get the sum. And so that is it for problem 34.